Jenny. I'm Amy Butler. I currently serve as a US CLIVAR panel member on the Process Study and Model Improvement panel, and today I'm guest editor for this edition of Variations on Stratosphere-troposphere coupling across timescales. Just as a brief overview, the stratosphere is a region 10 to 50 kilometers above the Earth's surface, and increasingly it's been recognized that variability in both the tropical and extratropical stratosphere can interact with and exert influence on the layer below it, called the troposphere, and on surface climate. So I'm very excited that US CLIVAR's spring edition of Variations and the webinar today is devoted to the topic of how the troposphere and stratosphere interact and how these processes could be improved in climate models. And we're lucky to hear from some of the leading researchers on this topic today. So we're going to start with Hannah Attard, who is currently a postdoc at the Naval Research Laboratory. And she will discuss stratosphere-troposphere coupling on short synoptic timescales. And then we'll go to longer timescales and look at seasonal influences on the stratosphere, namely relationships with tropical sources of variability such as the Madden-Julian Oscillation and El Niño Southern Oscillation, which will be presented by Chaim Garfinkel of Hebrew University. And then we'll look at relationships with snow cover by Jason Furtado at Oklahoma University. And then Joan Alexander from the Northwest Research Associates will discuss how the dominant mode of variability in the tropical stratosphere, the quasi-biennial oscillation, interacts with both tropical and extratropical tropospheric variability on seasonal to interannual timescales. And then on even longer timescales, we'll go to decadal and look at the role of solar variability on stratosphere-troposphere coupling, and John McCormick from the US Naval Research Laboratory will speak on that. And then finally, Isla Simpson from NCAR will talk about the role of the stratosphere on future mid-latitude climate projections. And so we hope you find this webinar informative, and please feel free to ask questions during the Q&A period.
Okay, thanks, Amy, for that introduction. So I'm going to be talking about connections between the stratosphere and synoptic variability. And I just want to acknowledge my co-author, Larry Coy from NASA. Next slide, please. So a quick background, Amy, introduced the stratosphere really quickly, but what I want to just say, on the right-hand side, you can see this is our 10 hectopascal, 60 degrees north, zonal mean, zonal wind, and in black is just our climatological mean. So you can see in the stratosphere in the wintertime, we tend to have westerlies. In the summer, we tend to have easterlies, but within the wintertime, we have a large variability. There's a lot of spread in what could happen, which is in the shading, you see kind of the percentiles in the minimum and the maximum. Overlaid on that in red is the 2008-2009 season, and you can see in that season we had a really strong polar vortex in the beginning of January with our zonal mean, zonal winds. And on the left-hand side, you can see just what this looks like in the longitudinally varying sense. So we have our polar vortex centered over the pole, cold temperatures, and our cyclonic circulation. So following this really strong vortex, we had this really rapid weakening that you can see. Our zonal mean winds descended or decreased in magnitude very rapidly. And on the next slide, you'll see that this is called a sudden stratospheric warming, when these zonal mean winds cross 0 meters per second. So when we have a reversal of the zonal mean wind, we have warming at the pole, a reversal of our temperature gradient, and negative zonal mean winds. And this happened primarily in the wintertime through upward propagating planetary scale waves from the troposphere. And on the next slide, we'll see that we can use heat flux as kind of a proxy for the wave activity flux that enters the stratosphere from the troposphere. So this is just a time series, a time height plot of our standardized heat flux anomaly for the 1998-1999 winter season, where we had an SSW on the 15th of December. So we're using heat flux because it's proportional to the vertical component of EP flux, which tells us about that wave activity entering the stratosphere from the troposphere, so we can understand kind of how we get these SSWs. So usually 100 hectopascals give us an indication of this kind of upward wave activity flux that we see. And you can see prior to the SSW, in this case, there's a lot of red, so we have positive heat flux anomaly, and these two yellow arrows are showing that we have this kind of upward propagation from the stratosphere into the, from the troposphere into the stratosphere. So we need really these planetary scale waves to propagate, but to get them, we can have kind of a synoptic events that positively interfere with the climatological flow to induce these upward propagating planetary scale waves. And on the next slide, we're going to define the two really types of synoptic events that we're going to focus on, which are blocks, which are persistent mid-latitude ridges, so high pressure systems that just stay put in one place for multiple days, and bombs or extratropical cyclones that deepen at least 24 hectopascals in 24 hours. And I'm sure everyone's been hearing about bombs in the media lately because we have one potentially occurring in the Midwest right now. But these are just extratropical cyclones. It's just a fancy way of talking about them. So as we can see now on the bottom here, I highlighted when we had blocks and bombs occurring in this season. So we have a block at the end of November that happened in Europe, and 2 bombs in December prior to the SSW. And we look at blocks and bombs because studies have shown that blocks often precede SSWs and are associated with these enhanced heat flux anomalies at either 100 or 200 hectopascals. And Coy and Pawson in 2015 emphasized the importance of extratropical cyclones in perturbing this wave guide. So as you can see, again, associated with these blocks and bombs, we had this upward wave activity flux. And if you go on to the next slide, I want to highlight that these events were actually associated with the top 100 hectopascal heat flux anomaly with respect to a climatology of synoptic events. So what I did was created a climatology of blocks and bombs and analyzed the 100 hectopascal heat flux anomaly following them and said, well, what's going on with the events that had positive heat flux anomaly and what's going on with these events that had negative heat flux anomaly? How can we tell when a synoptic event is going to be associated with this upward wave activity flux? So if we kind of group all together these top heat flux events and these bottom heat flux events, on the next slide we'll see we can look at the kind of composite flow associated with them. So on the left-hand side, this is just a schematic representation of the geopotential height for positive heat flux events. So these are blocks and bombs that occurred in either Europe, the Euro-Atlantic sector, or the Pacific sector, and were associated with the strongest 100 hectopascal heat flux anomaly following them. And in black, we have our 250 hectopascal geopotential height. In green, 100 hectopascal geopotential height, and in magenta is 10 hectopascals. So what you can see, highlighted by the low indicators that are overlaid on this plot, is that we have a nice westward tilt with height. We have a baroclinic kind of wave structure, which is really helping enhance that upward wave activity flux and those upward propagating planetary scale waves. Whereas on the right-hand side, now we have the anomaly negative 100 hectopascal heat flux events. So these are the synoptic events that were associated with less than normal upward wave activity flux. And although, again, you kind of see this, this low in the eastern hemisphere in the upper troposphere, in the stratosphere, the waves are really vertically stacked and centered over the pole, which means we have a much more barotropic or vertically stacked geopotential height field with height. So what this really suggests is that although the synoptic event itself is important, how it's interacting with the flow above it in the lower stratosphere and mid-stratosphere is also really important. The kind of precursor stratospheric state needs to be conducive for this westward tilt and upward wave activity flux. So on the next slide, we can talk about kind of the impact of these SSWs on the troposphere, because that's really what we care about mostly. That's where we live. So this is similar to the plot that I showed earlier that was the heat flux anomaly, but now we're looking at the standardized polar cap geopotential height anomalies. So what you can see, this is just our height field over the pole. We have the SSW that occurred again on the 15th of December associated with positive geopotential height anomalies that then descend downward following the event, influencing the troposphere. And at the surface, when you have these positive geopotential height anomalies, that's kind of analogous to a negative AO, which on the next slide shows that when you have a negative AO at the surface, you have this really wavy pattern. And when you have this wavy pattern, that's conducive for more synoptic events to occur, such as bombs off the east coast of North America, cold air outbreaks in Europe. You hear the beast from the east oftentimes used. So this kind of descending height anomalies from the stratosphere into the troposphere can impact our synoptic scale weather. And on the next slide, I just want to touch base really quick about the influence of the tropical stratosphere on the troposphere, and I know we'll go into more detail about this later, but the quasi-biennial oscillation simply describes the descending sign of the zonal mean winds over the equator. And so here's just a time height plot from 70 hectopascals up to 10 hectopascals, and I highlighted the easterly zonal mean winds. So you can see when you have this easterly winds descending, alternating with the westerly winds. And on the next slide, studies have shown that during the easterly phase of the QBO, the frequency of bombs in the extratropics has actually shifted equatorward, so the latitude of the onset of the bombing is farther equatorward than we would expect. But during the neutral phase of the QBO, so when the zonal mean winds are near zero over the equator, the frequency of bombs has actually shifted poleward. And the dynamics that drive this relationship is still an open research question. There's a lot of work looking at the interaction between the QBO and the MJO and how that could potentially modulate kind of these extratropical systems. So finally, on my last slide, I just want to comment on the predictability and kind of some future research directions. So a lot of ongoing work right now is actually exploring kind of this interaction between the stratosphere and the troposphere under anomalous stratosphere conditions that are not SSWs. So SSWs are the most extreme kind of disruptions that we can get in the stratosphere. We have that reversal of the zonal mean wind, but we can also quantify the movement of the polar vortex and the movement of the Aleutian high, which is climatologically occurring. So these are just a couple of studies that have talked about kind of quantifying that location and then how we can use this in the future to kind of look at the impacts of displaced polar vortex events on the troposphere. And specifically, studies have shown that there's increased tropospheric forecast skill when forecasts are initialized with SSWs, when an SSW did occur, but SSWs themselves are generally only predictable on synoptic timescales, although there's exceptions to this where certain SSWs have been forecast at 15 or even 30 days out. But if we can really improve the predictability of the stratosphere, that should also be able to improve kind of subseasonal tropospheric forecasts if we can better get this kind of descending height anomalies in our models to understand when we could have that potential stratosphere-troposphere interaction. So thank you very much for listening, and I'll take any questions.
Great, thank you, Hannah. So as a reminder, all of you guys are on mute, so if you have a question, use the raise your hand feature, and I will take you off mute to ask your question. You can also type it into the chat box. So any questions? Yep, I think it looks like we have a question from Mustafa. Let's see. Go ahead, Mustafa.
Good evening. Hello. Thank you very much for the presentation. I was just wondering, it's a very specific value that you mentioned that low pressure is deepening 24 hectopascal per, if I remember correctly, per 24 hours or something like that.
Yeah, so that bomb definition is defined in Sanders and Jocham 1980, I believe the year is. And it's actually 24 hectopascals in 24 hours relative to 60 degrees north. So you kind of do this correction to make sure you're comparing apples to apples at different latitudes. But that's a relatively arbitrary threshold, and it just kind of helps us give an indication for strong cyclones. But there's a lot of different ways that extratropical cyclones can be defined and different ways of looking at strong extratropical cyclones by the wind field, the strength of the wind field, and things like that, or the vorticity, the low-level vorticity. So this was just kind of an easy way of filtering through the many extratropical cyclones that we get in the winter season in the northern hemisphere.
Thank you.
Yep.
Great. Any other questions? Yep. Let's see, Mike Patterson has a question. Go ahead, Mike. Mike, I think you might be on mute on your end.
Oh, I am on mute. Okay. Hi, Hannah. Nice presentation. I'm curious on this last slide, this idea of extending the predictability of the stratosphere. Where do you anticipate that the predictability might lie? What mechanisms do you think might give us a longer lead time for actually predicting things like the SSW, or get us to that 15 to 30-day predictability timescale?
Yeah, I think that's a good question. There's a lot of different ways, I think, for potential improvements. There's a lot of discussion, I think, about vertical resolution and whether that plays a role. I think model top is an important one, especially with these S2S models when we try to forecast out at longer lead times. Because you're forecasting so long, a lot of these models have lower model tops. which I think is detrimental to trying to forecast an SSW. So that's one way, trying to get this wave activity flux and this upward wave activity flux from the troposphere into the stratosphere and forecasting that and understanding when that's going to occur is important. So that's what this was kind of getting at is, because what type of block, what do we need to happen to get that really upward wave activity flux? So I think that's a role that'll definitely also play a role in that.
Okay, well, thank you.
Mm-hmm.
Great. Thank you, Hannah, for your presentation. I think we will move on to our next one due to time. So our next presenter is Chaim Garfinkel from Hebrew University. Go ahead, Chaim.
Oh, hi, Jenny. Thank you for introducing me, and I'll be discussing the stratospheric pathway for the MJO and ENSO for boreal winter climate. And the main message of this talk is that tropical convection, both El Nino and Managilian oscillation, can affect extratropical climate, both through its tropospheric cloud connections. For example, the sort of well-known PNA or well-known wave chain from El Nino to the western U.S. In addition to that pathway, there's also a stratospheric pathway that El Nino and the Managilian oscillation both affect variability in the polar stratosphere that Hannah introduced. And that once the polar stratosphere is affected by El Nino or the Managilian oscillation, they then influence the North Atlantic and Eurasian sector. And so let's dive in. So just to show that there's a significant connection between Managilian oscillation and variability in the stratosphere, and just to show this connection, in this figure, I'm showing the phase of the MJO before sudden warming. So taking all the sudden warmings that have occurred over the past, let's say, 35 years or so, and looking at the phase of the MJO. So if you have MJO phase 6, 7, and 8, that's typically when you have convection in the West Central Pacific. Phases 3 and 4, we have convection in Indian 2, 3, 4 in the Indian Ocean, and 4 or 5 is already getting closer to the maritime continent. So in the 12 days before sudden warming, MJO phase 7 and 8 typically occur more often than the climatological occurrence. If you look, let's say, 13 to 24 days before sudden warming, phase 6 and 4 and 6 occur more frequently, and phase 1 less frequently. If you look a month before sudden warmings, then phase 2 and 3 occur more frequently. And so the potential for predictability exceeds 1 month. And in particular, if you just count sudden warmings that are preceded by these various phases, more than half of these sudden warmings that have occurred since over the time period we have good MJO data were preceded by one specific phase of the MJO, so phase 6 and 7. And so, for example, just to give an example, the sudden warming that occurred about 3 months ago fits in this category. But not so much in this category was one that occurred in, I guess, a little over a year ago, the one in February 2018, fits in this category quite well. Let's move to the next slide. And so once the polar stratosphere is modulated by the MJO, the impact propagates downwards to the surface, like we heard about briefly. This is, for example, showing sort of an index of variability. This is polar cap height. This is sort of an index of changes in the strength of the polar vortex in the stratosphere and changes in the latitude of the jet in the troposphere. So when you have a MJO phase 3, about a month later, there's a weakening of the vortex. And this weakening of the vortex propagates downwards in time towards the surface. And then about 50 days after MJO phase 3, there's a significant negative phase of the Arctic oscillation, or NAO. And so this is longer lead times than we typically think of the NAO being predictable. So it's 50 days in advance. There appears to be some predictability in the question and associated with the MJO through the stratosphere and then back down again. So the question is whether the impact of the MJO on the surface can be separated from the impact of the MJO on the surface through the stratosphere can be separated from a direct tropospheric route of the MJO on the surface. So, for example, if you have MJO phase 6 and 7, MJO phase 6 and 7 can impact the North NAO perhaps directly. MJO phase 6 and 7 can also impact sudden warmings, which then impact the NAO directly. And so you want to try to decouple these various routes. For example, is the MJO connection to NAO an artifact of the influence of the MJO on the stratosphere? In other words, is this direct pathway, how strong is this direct pathway? Is it weak? How strong is it relative to this more of an indirect pathway, but perhaps a stronger pathway? And that's what we're trying to isolate. So which of these pathways dominates? And so the way we disentangle these various these pathways where MJO is directed in NAO versus MJO affecting variability in the stratosphere, which then in turn affects North Atlantic oscillation or Arctic oscillation, is by separating MJO events into two categories. The MJO events that were followed by a sudden warming, and there's basically 12 of these events that we've categorized. MJO phase 6 and 7 events that were not followed by a sudden warming. And we can then look at the surface impact separately for these 12 events and then these 87 events. And what I'm showing here is the first geopotential height at 500 hectopascals for the MJO with MJO with a sudden warming following, and then the MJO without MJO phase 6 and 7 that were not followed by a sudden warming. And you see nothing here, and that's by design. These are relatively late lags, but even earlier lags, it's still very weak. In contrast, if the MJO affects, if the MJO leads to a sudden warming, you see very strong impacts. In this case, geopotential height at 500 hectopascals. About a month later, sort of a classic negative NAO impacts also over North America as well. And so if the MJO phase 6 and 7 does not have a stratospheric anomaly, in contrast, there's basically nothing at these long lags, and even earlier lags, it's much weaker than when you have a sudden warming. And so this is height in upper troposphere. Maybe we care more about surface temperature. Here I'm showing surface temperature for the MJO events that were followed by a sudden warming, and the MJO events that were not followed by a sudden warming. And again, we see basically nothing here, whereas in contrast, when MJO led to a sudden warming, we see strong impacts cooling over the US, cooling over high latitude Eurasia, warming over eastern Canada, and warming over the Middle East. And so this looks almost like a classic impact of a sudden warming on the surface, where you have cooling in this region, and warming here and warming here. And so a similar story applies for the ENSO as well. So let me just show that relatively quickly. So El Nino leads to enhanced sudden warming frequency. The one here I'm showing is a basically 41 realizations of the observed atmospheric response to a bunch of to 30 years of SSTs. Basically a bunch of about 6 or so El Nino events. And about 8 or so La Nina events over the past 30 years, and some neutral events thrown in as well. And this is just the sudden warming frequency averaged over each of those 40 realizations. And the key point is that for El Nino, there's an enhanced sudden warming frequency. So this is the number of integrations that show a particular, it's a histogram of sudden warming frequency for El Nino, for neutral, and for La Nina. And for the mean sudden warming frequency for El Nino is almost 1. Neutral is somewhat lower, and La Nina is somewhat lower than that. There's some discussion in literature about observations for La Nina. This is something that's been the subject of a lot of work, is understanding why the observed La Nina SSW frequency is so high. But either way, at least we see an increased sudden warming frequency for El Nino. And my last slide is this then impacts the surface. So if you look at, if we take all El Nino events that were followed by sudden warming and that were not followed by sudden warming. So in the North Pacific sector, we see sort of the classic wave train pattern. In the European sector, North Atlantic, we see this strong negative NAO in this region here, whereas if there was no sudden warming, we see something very different. And this leads to impacts on surface temperature as well. Cooling, so sort of classic sudden warming response with cooling here, a little bit of cooling there, warming here, and warming here. Whereas if there's no sudden warming, the temperature anomalies are very different. So just some take-home messages. So the stratospheric route is crucial for the extratropical surface response to both the MJO and the ENSO. However, there are so many open questions. Anomalous convection during the phase of the MJO that most strongly affects the vortex is somewhat different than where the fraction appears during El Nino. Low-thought models can miss some of these effects. Basically, if a model doesn't have sudden warmings to begin with, they can miss these effects, and not all El Nino events and not all MJO events lead to a sudden warming, and understanding whether this is sampling variability or is sensitive to the detailed convective response is an area of ongoing work. And thank you. I'll take questions.
Thank you, Chaim. Do we have any questions for him? Reminder that you guys are on mute, so raise your hand or type into the chat box. All right, so we will go on to our next presenter. Our next presenter is Jason Furtado from the University of Oklahoma. Go ahead, Jason.
Okay, thank you very much for having me today. So I'm going to pick up sort of on what the last two were talking about, and really look at another boundary forcing that can sort of influence stratosphere-troposphere coupling, and in this case looking at changes in the Arctic cryosphere during the autumn. See if I can go on. Oh, there we go. So just as an introduction, I know Hannah talked a little bit about the annular modes. So what I have here is kind of like a 3D slice of the annular mode from the stratosphere down into the upper troposphere, just to make the point that a lot of times we look at these on planar views, but the annular mode is actually a 3D structure, and in the troposphere represents migrations north and south of the polar jet stream, whereas as we get into the stratosphere, really we're looking at pulsing or changes in the strength of the polar vortex. And of course, as we can see in the plot here, we get into the stratosphere, things are nice and circular and elliptical, but in the troposphere, things get a little wavy because of land-sea contrast and also topography. So how do these things talk to each other? How do we get this 3D structure? Well, the main way to do it is through vertical wave propagation. And here what I'm showing on the left is climatological wintertime geopotential heights of 500 millibars. And on the right is the climatological vertical wave activity flux, which is proportional to polar heat flux. And so what you can see, of course, is that in the climatology we have these sort of two big trough areas, one off of East Asia, the other one across the North Atlantic. And because of the trough and the way it goes through, those are also the sources of where we get most of our wave activity that goes into the stratosphere. And so you can see that on the right plot here. So in other words, a way to sort of enhance variability in the extratropical stratosphere-troposphere is really how do I get changes in these planetary scale waves. So how do I amplify or de-amplify these planetary scale waves? And so a lot of work on looking on both seasonal and also interannual variability is looking at forcings that can change these. And Chaim did a good job talking about one of them being ENSO, but like I said today, or my talk, I want to talk about a couple of other ones. So the first one I want to talk about is high latitude snow cover. And this is snow cover basically continental across Eurasia and North America. So the idea behind this is actually nicely summarized here in this schematic from the National Science Foundation. It's work that goes back really to the late 90s by Judah Cohen and has been continuing since then. And the original hypothesis kind of goes like this, is that during October, the snow cover across Eurasia expands rapidly climatologically. And sometimes you can get really rapid expanses. And once that happens, the cold dome at the surface, or the cold air at the surface will induce the Siberian high to amplify. And if you get anomalously high snow cover, you can get the Siberian high to amplify even more. And so that standing wave pattern that I showed in the previous slide, essentially you kind of amplify that. And so that's shown here where the high gets amplified, and of course downstream that means the trough gets amplified as well. Well, if you amplify that pattern, then more vertical wave flux goes into the stratosphere. More vertical wave flux brings more polar heat flux, heats the polar stratosphere, possibly causes a warming of the polar vortex, and then this downward propagation happens, and that's sort of the downward talk, how the stratosphere talks back to the troposphere. So the troposphere pushes it and the stratosphere responds, and then you can get this wavy jet stream that happens during the winter months. This is a process that takes a couple of months to kind of evolve. The other one is also late fall Arctic sea ice extent. And so here I'm showing obviously one of the extreme cases in September of 2012, but the idea here is actually similar in terms of the pathway, it just starts in a different way. So essentially what happens is that you have low sea ice or low Arctic sea ice And so what that does is actually enhances more latent heat fluxes into the overlying atmosphere, so you warm it. That warming actually acts also in the mid-troposphere by amplifying the ridge over northern Asia, and by doing that you then amplify this Eurasian ridge trough pattern, and so then the rest of the process here is just like in that schematic that I showed you. So the two actually share similar types of hypothetical forcing, just one we're talking about high snow cover and the other one we're talking about low sea ice. And there's been a number of papers that have discussed this both in observation and also in modeling experiments as well. So we have a lot of evidence here in observations for this relationship between snow and sea ice and changes in wave flux. But the thing I want to talk about a little bit more, and sort of my key question number 2, is how is this relationship actually modeled in our coupled climate models? And I'm talking about these models that we initialize and let them run for tens or hundreds of years. So the rest of this talk I'm actually going to be kind of comparing and contrasting how those different steps form in the different models. And so for this, what I've done is I've taken 9 models from the CMIP-5 archive, the historical run, so 1970 to 2005, forced with observed greenhouse gas forcing. Those are the 9 models there, but actually I'll be showing ensemble mean statistics for the rest of this talk. If you're interested in individual models, of course, you can contact me later. So the first I want to look at that first piece of the puzzle, sort of how does the change in snow cover and sea ice, how does that change the tropospheric circulation, the amplification of that ridge trough pattern? So what I have here plotted for the top is regression of November 500 hectopascal geopotential height anomalies onto the October Eurasian snow cover index. And on the bottom, the same thing except onto the sea ice index. And I've inverted the sea ice index so that low sea ice would go with the mechanism that I described above. And the plots on the left that I'm showing for now are from reanalysis. So these are sort of the observations, quote unquote. And so you can see clearly we get that amplification of the ridge here across northwest Eurasia. We get amplification of a trough here. We actually get a dipole across the North Pacific here, sort of this North Pacific oscillation pattern gets amplified as well. And when we do the same thing with sea ice, we get the same or similar type of response, amplification of the ridge here across the Barents-Kara Sea area and amplification of the trough over East Asia. We don't really get a response, at least statistically speaking, that's what the stippling represents, across the rest of the hemisphere. So sea ice tends to be a little bit more localized, where the snow cover tends to have a more hemispheric point of view. So how do the models recover this? So on the, if I can get this to click, thank you. On the right side is the same analysis, but now done for the CMIP-5 ensemble mean. And the stippling on the right here is a little bit different. What I've done is I've highlighted where 6 of the 9 of the ensemble members actually agree in sign. So not necessarily a pure t-test, but just where 6 of the 9 agree in sign. And you can see that in both plots we get very different responses. Certainly no amplification of the Siberian Ridge in the CMIP-5 ensemble in either case. A little bit of a case for the sea ice. We do see the amplification of troughing across East Asia, but actually we see the opposite here for the snow cover. So the models are not able to replicate sort of this initial snow to troposphere mechanism, sort of those steps 1 and 2 of the mechanism that I described above. So can we actually still get amplification of vertical wave propagation from the models? So on the left here, what I'm showing is a lag correlation plot with time on the x-axis, pressure on the y-axis. This is the vertical component of that wave activity flux, so proportional to polar heat flux. And on the top is lag correlation with snow cover. The bottom is the inverted sea ice index. And so you can see that in November and into December, we do get this amplification of, or positively correlated, so higher wave activity going into the stratosphere in response to higher snow cover. In the sea ice regressions, we see somewhat of a connection, although it's a little bit more diffuse and maybe occurs more in January, although none of these are actually statistically significant, and we'll talk about that at the very end of the talk. But the point is that once you go to the models again, you don't get those connections. So on the right, again, is the same analysis, but from the ensemble mean. And you don't see, you hardly see any amplification. In fact, you see a de-amplification during December for the snow cover. Some amplification maybe in the upper stratosphere in response to sea ice, but elsewhere it looks quite different. I guess that would be the main takeaway here. And we can do the same thing with the geopotential height. So this is that polar cap height diagnostic again, 60 to 90 degrees. north, average geopotential height anomalies, the same lag correlation, so with time again and pressure, lag correlated with snow on the top and the November-December sea ice index on the bottom. And so you can see the amplification of the ridge, the positive correlation here, warming of the polar stratosphere, and then some signature of a downward propagation, that negative AO signature coming to the surface. See the same thing with sea ice, although the significance really lags until January and February for that. And again, the models have a completely different solution. They actually show negative height anomalies that extend through the troposphere for the snow cover, and then the sea ice response is actually delayed quite a bit until February and March. So it's actually kind of interesting that we have this observed mechanism, and I should also mention some of those studies I said were actually what I'd call targeted modeling experiments. So these are experiments where people have actually taken models, prescribed snow cover, prescribed sea ice coverage, low sea ice coverage, and they're able to actually replicate this troposphere-stratospheric pathway and then the downward propagation afterwards, again being forced. And so we can get this pathway if we look at those, but if we look at these sort of coupled climate model runs, these CMIT-5, these long integrations, this whole entire mechanism is not present there. And so this becomes a problem, because if we want to use, for example, this mechanism for any seasonal forecasting, if we'd like to use it for climate projections, using the models is going to be difficult because they're missing missing this mechanism. So the last thing I just want to conclude with is sort of a couple of ideas of why we might be seeing this disconnect going on. And so one of them is actually that the CMIT-5 or the coupled climate models in general tend to have poor stratosphere-troposphere coupling dynamics. So what I'm showing here is actually a plot from a paper that I did in 2015 with a larger number of CMIT-5 models. And it's a lag correlation plot of essentially January geopotential heights at 10 hectopascals, lag correlated with the geopotential heights at all other levels. And so in the observations, we get that nice downward coupling, that sort of 3D structure like I showed at the very beginning, where we're getting downward propagation through the column. And that's very apparent throughout the observation. In the models, though, you can see that the propagation starts downward, but then essentially stops at the tropopause, and we never get this downward coupling later. So even if we were able to amplify the wave activity flux from enhanced snow cover, the models would still have a tough time getting the last part, sort of that negative AO signature at the surface. The second thing I want to mention is that maybe what we're seeing in the observations might just be actually a non-stationary or internal variability type of thing in our climate system. And this has actually been sort of also hinted at in that same 2015 paper where I looked at sort of these long 500-year plus integrations. But just as a snapshot example, I just want to show here the correlation between Eurasian snow cover in October and the average December, January, February surface AO index. And if you look at the period 1979 to 1997, which would be the period that the original work would have looked at, the Cohen and Takabe papers, that correlation was negative 0.61, which is significant at the 99% level, which is pretty impressive. If you look at the entire record from 1979 to 2018, the correlation is negative 0.3. But the issue becomes later. So this is post-1998, the correlation. And that's right, the correlation is actually 0. And so we could be actually just seeing internal variability with this mechanism, something that's happening where sometimes the relationship is there and sometimes it's not. And why that's the case is sort of unknown. And I'll just throw up the last slide and then open it for questions. But of course, what's going to happen with this mechanism in the future as we have polar amplification? And this is actually a very interesting question to kind of explore and kind of look at. So I'll end it there, and I'll take any questions.
Hi, this is Isla. I was just wondering, to deal with the internal variability issue, whether you've looked in large ensembles at how variable the presence or absence of this mechanism might be?
Yeah, so I have looked at the long, so that 2015 paper looked at the pre-industrial control runs, and basically you just see a huge spread in the relationship. So what I did was I divided into like 40-year segments to look at different periods, and you do see sometimes the relationship is positive, sometimes the relationship is 0, sometimes the relationship is negative. And I didn't really dive into sort of why that was the case in each of those periods, but it would be interesting to know. I don't I don't know. I don't know if it's something with the stratosphere. I don't know if it's something within the with sort of the atmosphere, some other boundary forcing that could be modulating this. I'm not sure.
Thanks.
Yep.
Any other questions for Jason? So Mustafa, I see your hand is raised. Go ahead.
Hello, thank you for the presentation. I wonder if the poor representation of the propagation of stratospheric waves to the troposphere in the CMIP5 models has something to do with vertical resolution in these models. Thank you.
Yeah, that could be. There could be other issues too with sort of feedbacks with the troposphere as well. That's still a question that a lot of people are still trying to look at. There's also lids, so high top versus low top as well.
Thank you.
And I see Amy has a question. Go ahead.
Yeah, I was just wondering, given that the targeted model simulations that have the observed snow cover in them are able to reproduce this, are there deficiencies in the CMIP5 in terms of snow and things like that that could potentially explain where models could be improved?
So I did quickly look. This was not set up, but I did look at the coefficient of variation in terms of snow cover, in terms of climatology, and so it turns out that the models actually have a pretty low coefficient of variation for snow cover. And so that could also play a role. So they may, climatologically, they just may not have enough of variability in snow cover to sort of capture this relationship as well.
Thank you.
Yep.
Okay, any other additional questions for Jason? All right, so I think we'll move on to our next presenter. We have Joan Alexander from Northwest Research Associates. So go ahead, Joan.
Okay, thanks, Jenny. This article was co-authored with Laura Holt, my colleague at Northwest Research Associates. It's about the QBO, the quasi-biennial oscillation, which is QBO for short, and it's a dominant and generally very highly predictable feature of the zonal-mean tropical atmospheric circulation. It appears prominently in the stratosphere between 100 and at least 10 hectopascal pressure levels, as shown in this slide here. In zonal wind, no filtering needed to see this oscillation. These are just monthly means from Singapore radio sound records shown here. The latitudinal width of the QBO varies with phase, but it's confined to the tropics. It's strongest within about 10 to 15 degrees of the equator. And the QBO appears in observations dating back to the mid-20th century, and it's characterized by these descending zonal wind shear zones that you can see in this plot, changing sign roughly every other year. Here, E means easterly and W means westerly wind. Its period varies, but it's usually somewhat longer than 2 years, and it's not locked to the seasonal cycle. It's well understood now to be a wave-driven circulation, a circulation driven by tropical wave mean flow interactions with contributions from both global scale equatorial waves, particularly Kelvin waves, plus there's a major contribution from a spectrum of small-scale gravity waves generated by the tropical convection below. So the QBO was thought to be highly predictable a year ago, or highly predictable in the past. I'll go to the next slide. Predictable a year in advance at least, but in 2016 there was an unprecedented disruption in the cycle that happened. It did not appear in any forecasts, and you can see it here in this time height series. So I'll say a bit more about that later. Today's topic is the impact of the stratospheric circulation, this stratospheric circulation pattern at the surface. So we're interested in its impact on seasonal forecasting and interannual climate prediction, its representation in global models developed for those purposes, back in the early 21st century, some clear associations between the phase of the QBO and winter weather in the northern hemisphere emerged. And that's illustrated with this figure from Thompson et al., 2002. The association was apparently related to the occurrence of sudden stratospheric warmings, which were described earlier in the webinar. And decades before this, Holton and Tan had realized that the QBO modulated the strength of the stratospheric vortex with a mechanism related to latitudinal steering of Rossby wave momentum fluxes, or so-called Lyson palm fluxes, either more equatorward in westerly QBO conditions or more poleward in easterly QBO conditions. So it's widely believed that it is through this basic mechanism that the QBO influences northern hemisphere winter weather, projecting most strongly in the North Atlantic sector at the surface. So that's the first category of influences. I should mention there is also evidence that the ENSO tropical extratropical teleconnections that Chaim spoke of are also modulated by the QBO. However, using observations alone, if you start splitting up the data into ENSO QBO combinations, and it's not very statistically significant, but models have suggested this link is there. So the second category of surface effects is modulation of tropical precipitation, and associations between the phase of the QBO and tropical clouds and precipitation date back to the 1980s and 90s. And there were notable reports of QBO effects in the 2000s on tropical cyclones, on ENSO precipitation, and on outgoing long-wave radiation, OLR, which is an indication of the intensity of deep convection. The figure here is highlighting results from a recent study showing a modulation of the strength of the Madden-Julian oscillation, the interseasonal precipitation pattern, whereby the MJO is some 30 to 40% stronger when the QBO is in its easterly phase compared to the westerly phase. So cause and effect has long been murky at best in these kinds of studies, since the QBO itself is driven by waves generated by tropical convection. However, recent idealized model studies are indicating, in fact, a causal effect whereby the QBO's known influence on upper tropospheric static stability can modulate tropical cloud depth and convection intensity. So I tried to go to the next slide and nothing happened. Try again.
Should be on the next slide now.
Okay, well, I'm not seeing the change. It's slide 6. Something might be wrong with my connection. Shall I just continue?
Yeah, I can change the slide for you if you don't mind.
Okay. It should be on slide 66.
Yep, the QBO surface influence pathways.
Okay. So there are a number of potential pathways for the QBO's influence at the surface, and they're summarized nicely, I think, in this recent paper led by Leslie Gray, which diagnosed QBO surface influences in reanalyses using multiple linear regression methods. And in addition to the polar route that I spoke of before, this Holton-Tan mechanism described with the blue arrows, there's also a direct tropical route, which I also mentioned. But this work by Gray and others recently have emphasized a subtropical route whereby the QBO induced mean meridional circulations affect the depth and strength of the subtropical jet, and with eddy feedbacks that communicate that to the surface and connect to polar and tropical latitudes. So these routes of influence are by no means describing the end of the story here. There's a lot of research going on, but it's really a beginning for further work on QBO impacts in seasonal forecasting and interannual climate prediction. Next slide. So this discussion about pathways of influence is not just academic, of course. It informs progress in long-range prediction. And there are a number of recent papers demonstrating QBO influences on forecast and prediction skill. And I've listed a handful here. Next slide. However, the surface effects of the QBO in the models, in the forecast and prediction models, they tend to be weaker than observed. So next slide. And we don't know why for sure, but it may be due to persistent shortcomings in the fidelity of the representation of the QBO in most models. In particular, the lowermost stratosphere winds, the QBO winds at those lowermost levels, tend to be too weak in the models. The QBO tends to die out as it descends and doesn't get as deep into this lowermost stratosphere as it does in the observations. And these lowest levels may be key for, certainly for the direct tropical influences, direct tropical route that I mentioned, and may also be important for tropical, extratropical teleconnection effects with stratospheric pathways. Another shortcoming is that the oscillation in the models tends to be too predictable, too repeatable from cycle to cycle. And this is likely due to the fact that the models rely on parameterizations of non-orographic gravity wave drag to generate the QBO. And these parameterizations, to more or less degrees, include fixed settings that do not vary with time. This 2016 disruption that I mentioned at the beginning is described in this figure on the right, and it's taken from Osprey et al. 2016. The analyses are on the left edges of the plot, and then there's a little white line gap, and then you can see the predictions after that. So the top slide shows that the prediction was for the QBO to continue descending, whereas on the bottom it shows that what actually happened is this disruption. But then in addition to missing the disruption, you can see up at the upper levels here, up in the above 20 hectopascals, or above about 25 kilometers, the models always predict the QBO to start to descend again, and it predicted it right after, or it was predicting it in the first case, and on the bottom slide again, it predicts it again after the disruption. But in fact, this descent did not resume until sometime early in the next year, in 2017. And this is likely due to the overregularity of the parameterized gravity wave forcing. So there are additional challenges in modeling a realistic QBO, probably including the need for fine vertical resolution. That's been demonstrated in a number of studies, and that's computationally expensive. And again, this need for more realistic small-scale gravity wave forcing. Next slide. So just in summary, here's a few key points. The QBO has significant links to northern hemisphere winter weather patterns and to tropical precipitation variability. These surface links suggest a pathway to improved seasonal to interannual prediction skill, but model links are weaker than observed. And limitations in the fidelity of the representation of the QBO in models may be responsible, but improvements will certainly require both very high vertical resolution as well as improvements in non-orographic gravity wave parameterizations. And I should also mention convective parameterizations in the model. That's all.
Thank you, Joan. Does anyone have any questions for her? It's a reminder to raise your hand or type something in the chat box. Oh, looks like Isla has a question. Go ahead, Isla.
Hi. Yeah, I was interested in what you were saying about the models being too predictable, and maybe you said this, but is that really just coming from the prediction of this one event, or can you see that it's too regular in the models compared to the observations kind of in general?
Yeah, the QBO itself is too predictable. Yes.
Okay.
The way models get QBOs nowadays, at least at sort of climate and long-range forecasting, seasonal forecasting resolutions, they have to have a gravity wave parameterization, and those are tuned to give a QBO. If they have a QBO, they're tuned. And so you try to get a reasonable QBO, and the only way you get sort of deviations from that are through the large-scale waves, which do naturally vary in the models. And for example, Kelvin wave variability can give you some variability about that, sort of more tuned looking QBO. But the Kelvin waves they're probably contributing about half of the forcing at best in the westerly phase, and very little of the forcing comes from anything but gravity waves in the easterly phase.
Okay, so even if you have like a gravity wave drag parameterization that is dependent on the convection, can you see a difference then, I guess, between parameterizations that depend on the weather itself compared to ones that are just there all the time? Well, for example, NCAR's model has that, so it's a fancy parameterization, yeah. But it's still too regular. I shouldn't speak on that. I shouldn't say that. I'm not entirely sure. I'm speaking more in general terms. Yeah. So, yeah, maybe I think I'd have to look a little more closely at that with that question in mind to see if that is true. The NCAR's QBO looks pretty good. Okay, yeah, and it does get. I think it has a couple of disruptions in like a long run. Yeah, I remember seeing that. Mm-hmm. Thanks.
Great, thank you, Joan. Any other questions for her? Due to time, our last and final presenter is Isla Simpson from NCAR. Let's see. Go ahead, Isla.
All right, thanks. So I'm going to talk about the role of the stratosphere in future mid-latitude climate projections. So there are many ways in which the stratosphere could be having an impact on our future climate projections through, for example, its mean state or its variability or differences in chemical composition. And so I'm not going to cover everything here. I'm just going to focus on one particular aspect, and that's the impact of uncertainty in future predicted changes of the northern hemisphere polar vortex in the wintertime and its impact on projections of tropospheric climate change. So here I'm just showing the CMIT-5 multi-model mean, zonal wind for the northern hemisphere wintertime from December to February, and pointing out the polar vortex, which we've already heard a lot about. So we're really looking at the impact of uncertainty in the future changes in the winds in this region of the polar vortex in the stratosphere and its downward impact onto tropospheric projections. So here I'm just showing the CMIT-5 multi-model mean future minus past difference in zonal mean, zonal wind. And so here future is the end of the 21st century under a high emission scenario. And so what you see is that there's strengthening of the subtropical upper tropospheric westerlies, and then there's a pretty clear poleward shift of the southern hemisphere westerlies in the troposphere. But when we look in the polar vortex region, there's not really much change in that region. But this region is characterized by a very large uncertainty. So here I'm showing the spread across the CMIT-5 models, and I'm characterizing that by 4 times the across model standard deviation in the future minus past difference. So you can think of this range as covering roughly 95% of the models. And so what you see is that the region of the polar vortex is characterized by a pretty large model spread. So I'm going to take as an index of the measure of the change in the polar vortex. I'm just going to take the average zonal mean zonal wind anomaly at 10 hectopascals from 60 north to 75 north, and I'll refer to that as the polar vortex index. And so here I'm showing that for all of the different CMIP-5 models. And so what you see is that they can pretty much be divided in two based on the sign of the response. So half of the models project that you'll have a weakening of the polar vortex by this measure, and the other half project that you'll have a strengthening. And then the solid bars are ones where the anomaly is significant outside of what you'd expect from the sampling of internal variability. And so there's significant responses on both ends of the scale. And then here, just with the H's and L's, I'm showing which models are high top and which models are low top, defining that as whether the lid is above or below 1 hectopascal. And so what you see is that there's not really a relationship between the model's vertical extent and the response. You've got high and low top models on both ends of the scale. So from this, we really don't know how the polar vortex is going to change in the future, because the models are really all over the place. And so the question is, what is the impact of this uncertainty in the future of the stratosphere on the troposphere below? And kind of a first attempt at addressing that question was this paper by Elisa Manzini and co-authors on the CMIP-5 models. And so what they did was they performed a linear regression across models onto a measure of change in the polar vortex, pretty similar to the measure I'm using. It just has they're using a slightly different latitude range, but it doesn't make much difference. They also first regressed out the contribution to spread from a couple of other factors they thought would be important, like the spread in tropical upper tropospheric warming and Arctic amplification, but that also doesn't really make too much of a difference to their conclusions. And so this is one of their main results. This is showing here, this is a regression across models of sea level pressure onto the measure of change in the polar vortex response. And so what it shows is that models that would have a relative weakening of the polar vortex compared to others tend to show a relative increase in sea level pressure over the Arctic and a decrease to the south. And this is projecting onto the negative phase of the North Atlantic oscillation. So from this kind of regression analysis, you have an indication that there's a relationship between how a model's polar vortex responds to climate change and then the circulation in the troposphere. And if we can think of that as really being a downward influence from the stratosphere to the troposphere, then since the models are all over the place in terms of what the stratosphere does, that could be contributing to spread among the models in their tropospheric climate change. But then, of course, an issue with this is that we don't really know from this regression analysis alone that this connection really represents an influence of the stratosphere on the troposphere, as opposed to the other way around, or some factor that could be affecting both separately. So what we did to try and contribute to this question is did some idealized experiments within one model, and our aim was to demonstrate that the relationships found in these across-model regression analyses really are indicative of a downward influence of the stratosphere onto the troposphere. And then we also wanted to try and quantify the magnitude of this effect within a controlled single model setting. And so I'm going to show some results from that. This is using a 46-level version of CESM. It's fully coupled simulations, and we're comparing 4 times CO2 with 1 times CO2 climate. But specifically what we did was we nudged our model to have varying representations of the stratospheric polar vortex change, kind of mimicking models on opposite ends of the CMIP-5 range. And this was just done with a simple linear relaxation of the zonal mean winds and temperatures toward a specified target climatology. So here's the response in our model of zonal mean, zonal wind to climate change under 4 times CO2. And then what we did was to just run another simulation where we nudged the stratosphere under 4 times CO2 and 1 times CO2 to the climatology of the free running runs. And this was just to check that you don't kind of have too many artifacts of this nudging on the response. So we're always going to be comparing one nudge run with another, and we only nudge the stratosphere. And so then what we did were these 2 other experiments where we nudged the stratosphere under 4 times CO2 to different states. So we made our model have a big weakening of the vortex, and we made it have a big strengthening. And so basically what we've done here is kind of our model, to begin with, sits kind of in the middle of the range of the CMIP-5 models. And we basically added perturbations to the stratosphere to increase this polar vortex index by 5 meters per second, or decrease it, so that we can make this one model kind of span the range of the CMIP-5 models in terms of what the polar vortex is doing. And just briefly, the structures that we imposed, just temperature and winds, just came from regressing those fields across the CMIP-5 models onto the polar vortex index. So by construction, the difference in our model experiments between the simulation with the weak vortex and the one with the strong is equal to the CMIP-5 regression onto the polar vortex index times 10. So what I'll do is just compare the difference between our idealized experiments with the weak and the strong vortex to the across-model regression of fields onto the polar vortex index times 10 and times -1. So we're looking at it from the perspective of what do you get with a relative weakening of the polar vortex. And so if this kind of regression analysis of Manzini et al. Really does represent a downward influence from the stratosphere to the troposphere, then we should find similar answers between these two things, because what we've done in our model is to perturb the stratosphere, and we hope that that will then produce the response in the troposphere. So I'll just show the results for sea level pressure. This is showing the CMIP-5 multi-model mean future minus past difference, so you can compare the magnitudes with that. This is reproducing basically Manzini et al.'s result. This is just the regression across models of the sea level pressure change onto the polar vortex change. And so again, what this is showing is the model that has a relative weakening of the polar vortex has a relative increase in sea level pressure over the Arctic. And then this is what we get in our idealized experiment, where we've imposed the stratospheric changes. And so these two things are in pretty good quantitative agreement. So we really can think of these sea level pressure anomalies that we get when we regress across models as being a downward influence from the stratosphere to the troposphere, because when we perturb the stratosphere, we can reproduce them. And then I just want to finish up by showing precipitation. So this is a CMIP-5 multimodal mean future minus past change in precipitation. This is the regression onto the polar vortex index across the models. And so this shows if a model that has a relative weakening of the polar vortex has a relative decrease in precipitation over Northern Europe and increase over the Mediterranean. And then here's what we get in our idealized model experiments. And for most of this domain, these are in pretty good agreement. And I just want to point out the magnitudes of this. So this is about 10 to 20% of the present day precipitation climatology of the Mediterranean. So it tells you that kind of the influence of the difference in polar vortex change on opposite ends of the CMIP-5 range can produce a difference in precipitation response that is of the order of 10% of the present day climatology, which is quite large for the Mediterranean. So why do we have such a spread? I think that's really still an open question. Many studies have discussed the influence of stratospheric resolution, but they don't really all agree. And it's pretty clear among the CMIP-5 models that there's no clear link between vertical resolution and how they respond. A couple of mechanisms have been proposed, and we've kind of been looking into the relative importance of these across the CMIP-5 coupled models. And it seems that neither of these kind of fully explain the overall spread that we see, and that's work by UTM Wu that's currently in preparation. So I'll just finish up with the conclusions that the models don't agree at all on how the northern hemisphere stratosphere will change in the future. This has a downward influence on the troposphere, and while the contribution to overall spread is small, the difference between models on opposite ends of the range can be of the order of 10 to 20% of the present-day climatology of the Mediterranean precipitation, which is pretty large. So we need an improved understanding of the reasons behind this spread, and hopefully the outputs for the DINVAR MIP activity will help in that. So I'll leave it there and take any questions. Thanks.
Thank you, Isla, for presenting. We do have one question up already from Osprey Scott. He asks, if one were to nudge the troposphere in a similar fashion to the nudged stratosphere experiments, what would one expect for the stratospheric response? I haven't done it, so I don't really know the answer, but I suspect it would have a pretty small signal. I mean, it's kind of, I guess it's probably equivalent to saying if you composite based on the tropospheric NAO, how big is it? Well, yeah, no, it's not really equivalent to that. I think it would be small, but because I haven't done it, I can't say. Great, thank you. Any other questions for Isla? see that Mike has a question. Go ahead, Mike.
Hi, Isla. So how well do these CMIP models reproduce the snow and the sea ice, or how they evolve? And do those then show an influence on, as we saw in an earlier talk, on the stratosphere? Is that captured well? Is that modeled well? Can you speak to that?
I guess I can't really speak to how well it's modeled, but I think Jason's talk kind of suggests it was not modeled well.
Right.
If I understood that correctly. And I think it does have an influence. So we've done kind of similar experiments with Pengfei Zhang, and he has a paper where he kind of made the Barents-Kara sea ice go away, and then had a free-running model, and then ran the model where he nudged the stratosphere towards the present-day climate, and found a very different response over Siberia. So that was arguing that the stratospheric pathway was important, and there was changes in the sea ice loss that were having an influence.
Right, so there can be sensitivity from the boundary forcing from the land or at the surface.
Yeah, we haven't, UTN has been looking into that, whether there's like a clear link across models, and it's not clear. Like in terms of one model might lose more sea ice, does it have a bigger weakening of the vortex? I think there's probably just many things going on that are contributing to this spread, that there's no one silver bullet that is going to explain it all.
Right.
Great. Okay. Thank you, Mike. Any additional questions before we wrap up? All right. Thank you, Isla, for your presentation. So I want to thank all of the variations authors for taking the time to present today, and a big thanks to Amy for helping put together this issue. We will have a posting of this presentation on our US CLIVAR YouTube channel by early next week, so stay tuned for it. So with that, thank you everyone for participating.